Okay, it's recording. Okay, so hello everyone. Thank you for coming today. So today we have another compiler talk. And so this time we've got Ian and Tim from Paradise. We're going to talk about LLZK, which is essentially a family of MLIR dialects targeting ZK circuits. And I guess Paradise is the main contributor. There's been some contributions from other teams as well. So it's a pretty fun, exciting project, and it's starting to be quite mature. And yeah, all the floor is yours.
Cool. Yeah, thanks, Alex. So yeah, we recently made the first stable releases of LLZK. So we wanted to take an opportunity to give a, I guess, a quick intro to LLZK for those who are not familiar with it, but then also just present the state of LLZK and its integration into the ZK ecosystem, and we'll mention some of the other groups, like Alex said, who have contributed to LLZK or started integrating LLZK into their ZK compilers or their analysis tools and stuff like that. Let's see. There we go. Yeah, so first I'm going to talk a little bit about just the motivation why we built LLZK. So there's a lot of fragmentation currently in the ZK ecosystem. So you have here like the various languages, each has its own compiler stack, its own kind of circuit rewrites, optimizations, and then its own, well, possibly common backends that it's targeting, like they may all generate R1CS or something, but also they may each generate their own specific type of IR target assembly or something for their ecosystem. So the main goal of LLZK was to kind of reduce the duplication here, bring together this fragmentation into a more unified, coherent IR, intermediate representation. One of the big problems we've seen with this fragmentation is that, like in ZK languages and in circuits, you have a lot of the same kind of vulnerabilities and the same kind of bugs popping up. And so each compiler stack would have to handle these bugs, or each static analysis tool that wants to target a different compiler stack has to figure out, okay, let me either figure out how to read in from this compiler stack or this language and handle these bugs, and maybe in a different way per compiler stack. And so there's a lot of this like duplicated effort, again, like we're seeing across the ZK ecosystem. And so again, we want to help solve this issue and hopefully reduce bugs overall and reduce vulnerabilities overall in the ZK ecosystem by unifying things and solving problems one time instead of solving problems every time for each kind of ZK front end. So this is kind of the architecture of LLZK. So you see some different front end languages listed in the blue boxes, and then there's a kind of translation step for each into the LLZK IR. But once you get there, then everything is in the unified stack, where you have transformation optimization packages, or passes, I mean, that are defined on LLZK IR. You have different backends or static analysis tools or verification engines that can all run on LLZK IR. So you're only having to implement these things once, and you kind of get for free every front end language that feeds into, or like that has a translation into LLZK IR. We have, I put the link down here. So I think the majority of LLZK stuff is now hosted in this project LLZK GitHub. And as we're getting contributions from other people, for example, a like front-end language or a back-end tool, some of them have asked us if they can port those into the project LLZK, not repo, organization. What's the right word for GitHub? So the project LLZK organization. And so we're kind of, yeah, as they contribute things, we're bringing them in there so everything's available in one place and easy to find. So I'm going to go a little bit into the IR itself. I actually will be showing a simplified version. So this is built using MLIR from LLVM. And so it is a bit more verbose with types, and I simplified this to fit it on the slide. And I'll show the actual LLZK, like LLZK and MLIR syntax at the very end. So you can say you've seen it, but it wasn't going to fit well on the slides. So this is on the left-hand side, SERCOM circuit, and on the right-hand side, the simplified LLZK IR. And so in LLZK, we organize subcircuits into structs, is what we've called them. So here you see the two templates from SERCOM are translated into two structs on the LLZK side. And then within the structs, you have members, and these hold the witnesses and the intermediates for those circuits. And so, again, from the SERCOM example, you see the output and then the return value, and then there's W1 and W2 are these two subcomponent get weight instances. I said these hold witnesses and intermediates. So you see on the red, there's this additional attribute pub. So that says this is a witness value, and the others are kind of internal intermediate values. And then the compute function holds the witness generation code. And so from the SERCOM, where you have combined witness and constraint generation code, that front end is splitting this out into a compute and constraint function. Some languages directly have that split out already, or some may be just expressing the constraints. And so you may have an empty compute function in that case. So yeah, here you see kind of calling the subcomponent computes, where getWeight.compute with the 99 input and the N0 input gives you W1, and then similarly to get W2, and then you take each of their subcomponent outputs and write it into the return array for this component, the main component. And so generally the compute function is, yes, creating an instance of the current component, assigning all of its members, and then returning that instance. So you see here the return type is struct main. The constraint function is taking as input that already constructed instance and the same circuit inputs. I think I forgot to mention that the parameters on each of these functions, the in array to a felt, is the circuit inputs. So the signal input in from the SERCOM side. And so here we're calling the subcomponent constraint functions with the subcomponent instances, W1 and W2, and the same inputs as before, and then adding these constraints that the output of the W1 component is constrained to the red index 0, and output of the W2 subcomponent is constrained to the red W1. And let's see. Yeah, so that is the basic overview of what LLZK looks like. There are a lot more details. Let me also, I said I was going to put the actual kind of MLIR code. So yeah, it's more verbose with types. It's going to span 3 slides here. The first slide, I have the get weight subcomponent. You also can see like something I didn't show in the examples. There's this extra poly template construct that things are wrapped in to represent more exactly. The SERCOM program had these like template parameters. And then here's the compute function of main. Like I said, struct new is creating the struct, and then all the middle of this is instantiating the different values of that subcomponent struct, and then at the end returning the filled in subcomponent. And then the constraint function is here. You can see some constraint EQ emitting constraints, function call into the subcomponent constraints, and then, of course, all the other nice stuff to read from arrays, read from the members, all the other necessary little tidbits. So yeah, that is the full example on those 3 slides. So I'm going to go into the front end translations a little bit more. So we have available now the SIRCOM front end. So that's the example I was showing you is from SIRCOM. We have a library for Halo 2 and Plonky 3, and another one for Airbender that allows you to generate LLZK-IR from those circuits. And our initial front end we created was for Zergen, but they have since deprecated that language, so it's still out there if anyone is still using it, but they've moved on to represent their circuits in a different way. And when we were putting together front ends and thinking about what features to include in LLZK-IR, we kind of had this guiding philosophy that we want to have as much support as possible in LLZK-IR so that the front ends themselves are simple and they can be more like straightforward one-to-one translation. So we don't want them to have to do a lot of transformations on the code to get it into some format that is compatible with LLZK-IR. So like I mentioned with the example earlier, we have that poly template, which allows you to directly translate what the templates with parameters from SIRCOM into LLZK-IR. And in a little bit, Ian is going to mention how we then kind of can lower these higher level features into lower level representations. But we want the higher level features to be there for to make friendly front end transformations. And there's also, I don't have it on the slide, there's a Noir front end that's currently being worked on. So we should have that coming available soon as well. And then we also, I wanted to mention that there are some folks from Fractalize who are currently using this SIRCOM front end, and there's also some folks working on a verification backend that's using this SIRCOM front end. So yeah, we have 2 people who already, or 2 groups who are already integrating the SIRCOM front end into their workflows, their pipelines, and have helped us to fix some issues that came up or some other support issues. So there's good support and usage on the SIRCOM front end side already. So yeah, now I'm gonna hand it over to Ian, who's gonna talk a little bit about what goes on in LLZK core itself.
Yeah, and going along with that whole philosophy of trying to have all of our various levels of features in the IR rather than having to lower everything in a particular front end, we're also trying to build up a library of different program analysis and transformation utilities so that regardless of a particular front end's entry point into LLZK, whether that be because at the SIRCOM level we can have templates, we can have multiple different kinds of structs versus something more like Airbender, which we don't even have. We're not emitting templates for. Everything is already a flattened struct, and it doesn't really use arrays or complex data types that much. And so regardless of what your entry point is for your circuit representation, you can lower it to, the goal being to be able to lower it then to whatever state you need for a particular backend, whether that be to lower it to R1 CS friendly representation or just have it available to the limitations of whatever static analysis tool that you may have downstream or program verification tool. So with that, there we go. All right. So yeah, we have a library of different transformations that we've already built up, and this is just an example of some of them. We have a few more in there as well. So if there's ever, and just a general point too, is if there's ever, if somebody's using the library and they ever have a question about, hey, is there a feature that can do X for me, feel free to reach out and ask, because sometimes something's currently in development, or maybe the documentation isn't linked properly or something. We've had a couple issues with that where our documentation didn't get propagated to our Doxygen website properly. So feel free to always ask if there's something available, because sometimes we have some other stuff that we're not going to talk about today. But we have a flattening pass for one example that both can instantiate templated structs, so you can make them concrete and put in all the specific instantiations of those structs. So you're performing a program analysis and you don't want to try to be generic to whatever your parameters are. You can flatten that and make it easier to perform analysis. And of course, we can also do loop unrolling. Also very helpful for different static analyses, flattening to different backends. We also have a struct inlining pass. So I believe we use this for our R1CS backend as well, where we don't, we want to represent everything as just functions rather than having complex data types. So we can inline subcomponents into a single struct, and then from there we can eliminate structs. We can also flatten arrays to scalar values, flattening those with our array to scalar pass. And we also have even a degree lowering pass. And in this in particular, we do use for the R1CS backend, where we lower the degree of polynomials so that we allow it to, conform to the R1CS specifications. And on top of this, on top of the passes that we've built specifically for converting our custom LLZK dialects, we also get a lot of transformations for free, or at least partially for free, with the LLVM infrastructure. The dialects that we implement and the ops that we implement in those dialects have operation interfaces that come from MLIR, and those operation interfaces allow us to do custom standard kinds of transformation passes, like common subexpression elimination. You can do dead code elimination. You can do canalization passes, and we've even implemented extensions so that you can do constant propagation over finite field arithmetic as well. And so you get a number of these kind of generic, standard program compiler optimization passes that you would from standard compilers out of MLIR as well. And this is, in part enabled by having traits that you can implement on the different operations. You can mark them as being pure types of operations without side effects. And so that allows you to, do things like, get common subexpression elimination and that kind of thing. So not only do we have some custom transformations that we're building, but we get a number of nice ones for free or mostly for free, like I said, from MLIR, because there are a couple places where you need to implement your custom functionality, but otherwise the framework of the base implementation of the pass will take care of that for you. So there's a number of nice things that we inherit from building off of MLIR as well. That also leads us to different kind of program analyses we can do, and we've used these both for building other transformations, as well as other static analyses that can be used in downstream tooling as well. So we have a call graph analysis. This is just an example of some of the passes, again, that we have built. We have a call graph analysis that we've used, and we actually did port this from, MLIR does have a built-in call graph analysis, but we have some custom symbol lookup logic in LLZK. And so we customize the call graph analysis to just be able to work with our symbol resolution logic. And so we have a call graph analysis. You can see, the reachability of different structs or free functions in the program. We also have what is called a source reference analysis, and we've used this. Basically, this maps intermediate or static assignment values to sources in a circuit, meaning signals, members of structs that have been read from, if they derive from a function argument. And this is useful in a number of debugging passes where, say, you have an under-constrained signal, an under-constrained value, and you're trying to figure out where it's actually derived from, so you can omit debug information saying this, the signal's unconstrained and it's defined over in this part of the circuit. So we've used that for a number of different static analyses. We have what is called the constraint dependency graph analysis as well, and this computes a transitive closure over constraint operations. So it tells you, in effect, what signals are connected to what other signals via constraints. And in particular, we have used this to build a number of unconstrained analyses that show, because it allows you to figure out for a given signal, is it constrained by another input? Is it constrained by purely constant constrained? And if not, that may indicate some kind of vulnerability. And so this can be useful at a course level for figuring out what signals are connected to what other ones by constraint logic. And we've also implemented a interval analysis or range analysis. And this is more of a lightweight static analysis that computes some approximate value ranges over signals based on both, and this works for both compute and constraint logic using, of course, constraint emissions or witness generation operations or even assertions that are present in witness generator code as well. And we've used this to figure out when potential signals may potentially be out of bounds depending on data types. So, and like I said, this is just a number of analyses that we have built that have been useful for our own downstream tooling. And so I just wanted to give a little example of what some of these actually looked like. When I was talking about the constraint dependency graph, you can see that basically the idea is telling you which signals are connected to which other ones. And so you can see here that the constants have been constrained to the different elements of the array here, and the constraint dependency graph traverses the emitted constraints to figure out which sources have been constrained via those operations. And so you're able to, it traverses those static assignment values back to the sources via the source reference analysis to show that it's, they're derived from the input arguments and from the poly template parameters as well. And so you can see we have the documentation for these up on our LLZK website as well, because we have a linked in the GitHub repo that Tim shared earlier. We do have a Doxygen website that has generated the documentation from this from the table gen in MLIR. So that should be available. And of course, if there's any issues with that documentation, please let us know and we can help resolve some of those. And I also just wanted to talk about the interval analysis that we compute as well. It's doesn't give highly precise intervals because the idea is to just derive a single interval for every value. So you could always have split intervals where a single value may take on multiple different ranges, but we combine them into single ranges just for efficiency. The goal is to give an approximate values, but we're able to do interesting analysis with this. For example, there are many circuits do some kind of byte decomposition to prove basically that these input bytes can be aggregated into a larger, let's say a 16 byte value, as is in this example. And we can actually derive that those intervals via this constraint logic, where we can see that, okay, yes, the two input bytes are actually bytes, and the aggregated value that is then created is actually a 16-bit value. And we have a number of different interval types that we implement, kind of based on their size and where they're positioned in the prime field. And we implement we implement 4 different basic interval types with this that either span positive and negative values, or only positive sub half prime, or over half prime, or somewhere in between. And we omit some of these kind of larger intervals that are like more than half of the prime field range, because it doesn't end up leading to a very useful analysis when you say, well, it could be basically the entire prime field range. So this is just a brief overview of that, but if you have we have documentation specifically on how these are derived in that past. And of course, if you ever have any questions about these things, feel free to post issues or anything like that as well. And so that is the overview of basically kind of the inner toolbox that we have of different transformation passes and analysis passes. And so I'll start wrapping up here with a discussion of some of the backend targets that we support. Once you've done all your transformations and want to, export to a different tool or backend format, and sort of what we support now, as well as what is coming up soon, because a number of our upcoming work items are related to our backend support. And so we have a number of things here that are coming up either from as a product of our ongoing grant or from our external contributors as well. So we have a few conversions from LLZK to other MLIR dialects. So currently we have defined in the LLZK library an R1CS dialect. So it's a MLIR representation of R1CS. We will soon have a lowering from this R1CS to the actual binary R1CS format, and that should be coming in the next couple of weeks, I believe. And so then you can actually take LLZK and lower it directly to the R1CS binary format. And we also have in the repo, we have an ZK lean backend, and this was a contribution from the folks at Galois. So that was very much appreciated as well. Coming up soon, we have a conversion to the SMT dialect, and the SMT dialect is actually upstream in MLIR as well. So that's a conversion to backend format that's actually supported by base MLIR, and then from there you can lower it to the SMT lib. And so we're working on that. We also have some passes that we're building soon to lower the witness generation code specifically into built-in MLIR dialects like the arith dialect. There's even an LLVM dialect that you can lower into. And we're lowering those because once you lower into those core MLIR dialects, you can do MLIR has built-in conversions to CPU code as well. So you can do that to either do an interpreter or use their JIT engine as well. So that's coming fairly soon. We have some of that up in review already. And the team over at Fractalize as well is working on a conversion for the witness generation code into stable HLO for an accelerated witness generation execution on so GPU accelerated witness execution. So that's also coming soon. It's pretty exciting work from the folks at Fractalize. So those are some of our backend conversion targets. And we also have a number of analysis tools that we support and are going to support soon as well. We have a few in-house analysis tools that are available. So for example, we have a static analysis tool, ZK Vanguard, that Veridice has on our platforms that we use to identify some common vulnerabilities, both in witness generation and constrained logic. So for example, you have out of bounds errors or under constrained circuits, unused inputs, that kind of those kind of common vulnerabilities. And we also have a conversion from LLZK to the PICUS constraint language, PCL, which our formal verification tool, which is PICUS, uses to formally verify under constrained circuit vulnerabilities or the lack thereof. So those are some of the tools that we have available now, and there's a number of exciting things that are coming pretty soon. And I mentioned this briefly earlier, but as part of our current maintenance grant, we are working on a witness generation interpreter. So you can do some easy debugging for witness generation code. And that runs in both an interpreted mode, and MLIR also provides an execution engine that has that is JIT backed, so you can do just-in-time compilation to CPU code. And so there's a couple of different options for how you can run LLZK that way. So that's under review and should be coming soon as well. We're also working on, here at Veridice, we're working on a tool called LLEQ, which is a semantic equivalence checking tool. which works on verifying equivalence between witness generation logic and constraint generation. And this is also the product of another grant, and so this should be coming soon and should also be open sourced in the project LLZK repo. So that should be coming soon. And of course, also as Tim touched upon earlier, the Costa group is working on building Avazar, which is a tool to verify semantic equivalence between like the R1CS constraints and the SMT lowering of the witness generation logic. So that'll be an exciting tool as well to do some equivalence between witness generation and constraints, which has been the source of a number of circuit vulnerabilities over time. So there's a number of cool and useful security tools that are coming that are supported by LLZK.
I want to add in, Ian.
Yeah.
I think we have another presentation upcoming towards the end of June
right.
on LLEQ. So it should be available and coming later in June, and then we'll have a presentation as well on that.
Yes. Yeah. I think I had a slide at one point that had upcoming talks, but yes, you were correct. There's an upcoming talk on that, and there's also going to be an upcoming talk in June on the specification language that we are building. So we're building a specification language that works with LLZK, and we're also building a verification dialect for LLZK for building specification-based tooling as well. But we will have a talk on that later in June. So I will leave you in anticipation for that. Finally, just before we wrap up and take any questions that anyone has pending, we just wanted to acknowledge all of our contributors and collaborators that we've had. The Ethereum Foundation, of course, has given Veradice several grants for supporting LLZK and some related tooling. So, of course, we're very grateful to them for that. As I mentioned earlier, the ZK Lean backend and transformations were built by Galois. And we also have a RAM dialect that was contributed by Relabs. And the stable HLO backend as well from Fractalize is going to be integrated soon. And they're going to migrate that to the project LLZK repo as well once they've completed that implementation. So we're very thankful for all of those contributions and the support and the use of LLZK. So and as going forward as well, we're definitely very open to contributions. So throw us issues, throw us PRs, and we're happy to review or any questions or comments. You can reach us in whatever formats you want, and we'd love to talk to you about it. So I think that wraps up what we were going to talk about today. Happy to take any questions now.
I just wanted to add on to what Ian was saying. Like we loved that we have some contributions coming in already, because like I mentioned at the beginning, like our goal and our vision when we came up with LLZK is to help integrate and like bring the ZK ecosystems together into a unified framework that can really help reduce bugs or reduce vulnerabilities and simplify implementations of tools and backends and stuff.
Yeah.
So the more people we can get starting to use it and contribute to it, the more we can move towards achieving that vision we had starting out with it.
Yeah, and one thing that we've done intentionally is this is not like all the LLZK stuff is in Project LLZK. It's not a Veradice product. It's its own open source ecosystem. We want other contributors. We want other people to work on it and to use it. And so we want community driven like features to be implemented as well. So I think previously there was a like the RAM dialect, global dialect, I think something else as well. I can't remember what other dialect, but these have all been community driven features. And so if there's something that your language, your circuits want to support, your language needs, like we want to implement it, we want to help implement it. So because we don't want to just support our use cases, we want to support all the use cases that we can. So Yeah, that's our part of our philosophy.
Yeah, if we have any questions, we can answer those, maybe try to answer them. Feel free to jump in if you have one, but otherwise I'll start. Just, yeah, again, thank you to the Ethereum Foundation for the funding that they provided to get LLZK off the ground, and for their help, and for Alex's help in bringing in and getting people to start using LLZK. And again, thank you to the other teams that have started to contribute already and start using it.
I have a quick one if no one is
Yeah, go ahead.
It's more kind of curiosity in the language design. So it's always very difficult to decide kind of what goes in as a construct and what doesn't in a language. And I think that mainly this means that whether you're gonna take in the complexity if you offer a specific feature in the language and just like the backend will deal with it, or if you don't put that construct that, and then the front end will have to deal on like with the specific complexities related to that construct. How did you guys decided what goes in and what didn't? Was it like talking to the different like stakeholders and different people that were building the languages that you were kind of planning to map from? And were there like constructs that you were considering putting in, but the handling that on the back end was such a like nightmare that you decided to kind of basically leave it out?
Yeah. I'll go ahead first, then you can let it in. Yeah, I was gonna say we kind of started with, like I mentioned, Zergen and SIRCOM as like what, looking at those languages and like what is the core of a circuit and what is the core of a ZK program, essentially, to try to figure out like what are the base features we need to add. And then as we started to work on the actual SIRCOM front end and work on some other front ends, we came across, hey, this front end would be a lot easier to implement if we had templates, if we had global variables. And then making that realization, then we moved in to think like, okay, how will this affect the LLZK IR overall? And is there a way we can lower these representations into this kind of base set of ZK operations? Is there because we don't want to end up in a state where the back end gets something and like, hey, what do I don't know what to do with this. Like we want, and MLIR has these nice ways to define lowering passes. And so that's kind of our practice with thinking about new features, is like, how can we lower this feature to kind of the base ZK circuit?
Yeah, and with that too, one of the nice features about, and one of the things that we've done intentionally with our design is LLZK is not a single MLIR dialect. It is multiple different, we have what, like 10, 12 different dialects at this point. And most of those encompass a particular kind of feature. So we have a dialect that is the struct dialect that defines the struct type, struct members, a function dialect. We have a globals dialect, an array dialect, the field element dialect, the templates or the polymorphic dialect that has templates and template parameters. And the nice part about doing that is that for a given backend or conversion pass, you can mark what features are like legal or not legal. And so you kind of have an explicit interface, or an explicit way to say like, this backend is going to support this subset of LLZK features. So if you want to use this backend, you have to define a lowering pass that, and the lowering passes are defined in such a way that it's, as an input, it takes this dialect, and as an output, that dialect is removed, right? And so you can have a set of passes that, okay, if my backend doesn't support structs, I will use the, you know, struct, or like, you know, the scalar pass or flattening pass, whichever one. You know, the struct elimination pipeline to ensure that when I get here, all of the structs have been removed. And so we can manage complexity in that way as well. As, you know, if you go and define some really high level dialect somewhere, you put the pipelines in place to lower it, and then everything, you know, beyond that will be supported. So it gives us a clean way to define kind of feature boundaries and feature inclusion as well, which is nice.
Yeah, and this list of passes that Ian talked about on this transformation slide is essentially the R1CS lowering pipeline. So yeah, like removing templated structs and loops so that everything is concrete representation, like fixed sizes and fixed values, and then inlining structs. So you just have like a single function, array to scalar, so making everything into scalar values to remove arrays. So that's removing that like array dialect that Ian mentioned is completely removed by that pass, and then degree lowering. So that gets it down into the representation for the R1CS dialect backend. But yeah, other backends may be able to handle something at a higher level and not need to go all the way down to that representation.
Thanks.
I would say, yeah, and I would say too, just as a point of you know, some of the most complex features I think that we've had to deal with were because they were not clearly specified by the front ends. There's been a couple cases where the behavior was a little bit unclear in the front end language. I think in particular for like Zergen, there was a couple of confusing things, and that's what made it harder to implement on the back end. So generally, I think we found that if features are fairly well documented in front end languages, we've figured out a solution for implementing them in LZK.
Cool, thanks.
Yeah.
Hello. I'm a bit curious about this transformation, the array to scalar transformation, because yeah, it's something that might be useful for us for this other project we are running on LLZK, and I would like to know a bit more what how do you handle? I understand that this removes the arrays, but how do you handle then the, let's say when you index with some other variable or signal or whatever? So just to know how you handle this and maybe compare to things that we have been doing, but maybe we can reuse yours. It's just to know a bit more.
Yeah. So the places, like the important places, I guess, that you may have arrays would be like members of the structs, or the inputs to your circuit, or subcircuits may be an array. And so in both of those cases, we're kind of multiplying the size of those constructs. So like if you have an array member, for this pass, you have to have the concrete version with fixed sizes. So you know, like, okay, this array contains 10 elements, and we're going to add 10 members to the struct, then one for each element of the array. And the same thing for if it's like an input to a subcircuit, we're going to add more parameters to that function to handle however many inputs were in the array. And so it can obviously, like if you have a circuit with very large arrays, that can explode the number of inputs and the number of members in your fields, or members in your structs. But we've had success with using that in the R1CS lowering that we've done so far. We haven't had that be a major blocker where you have way too many input parameters or something to a function.
Okay, but this is for R1CS, but for the witness generation code, I mean, well, I'm a bit more curious about the accesses to the array. I mean, when you want to access some position, and this position maybe in the witness generation code depends on some other signals or variables. How do you handle this in this particular case?
Yeah, that one is a bit more tricky. Let's see, it's been a while since I looked at it. I don't remember if we have added support for that, but the way you could support that would be like, yeah, adding a big switch statement essentially to handle that dynamic input, determining which array value you're reading, or which then scalar value. So like a big switch statement to pick out the scalar value.
Okay, thanks.
Yeah, I think
By the way, if you can just share the link to the part where you have this pass, it would be nice, because we will look at it and see.
Yeah, let me look for it.
Thank you.
Mhm.
Thank you for the talk, by the way.
Yeah, I'm gonna finish finding that for you. But if we have any other questions, we can take those, or
Yes,
otherwise
you.
I'll just thank everyone for coming to hear about LLZK today. Okay, I dropped the link to where the pass is implemented for you there.
Thanks a lot.
Yeah.
Cool. I think if we have no more questions, we can go ahead and wrap up the meeting then.
All right. Thank you. Thanks, everybody.
Thank you. Thank you.
Great. Yeah, thanks.
Thank you.